How are you all? Dave Rossio here from KPM Fuel Systems. We've brought you back into our fuel room. We want to show you a little experiment today. We're gonna test and show what our KPM fuel system controller can do for you. We call it a PWM controller, and we're going to try to explain what it does. It's included in our kits as an option on our 1500 module and as a must for our 2200 and 2700 horsepower kits. So I've got our simulator set up here today, and what we're going to do, we're going to simulate a return system, and we're going to simulate a PWM system and explain the differences between the two. Righto, so we've got our simulator set up for firstly a return system. We normally don't do that. We don't utilize a return system, but as an experiment, as a means to show you the difference between our systems, we want to simulate a return system. So we've added a return fuel pressure regulator. So what we've got is our KPM 1500 module there, pumping fuel through our flow meter. It'll record how much flow it's flowing. It'll also record, once we turn it on, the fuel pressure, and also this is where we're really going to focus in on the fuel temperature. It'll come back out through the regulator. We're going to set that to 58 psi. Pretty basic running pressure on most OE vehicles and aftermarket vehicles. You can set it to what you like, but we've set it to 58 psi. And obviously we've plumbed it so it returns back into the module like your aftermarket return system. Now the reason we're going to do a return system versus a PWM control system is to try to explain the subtle differences. The return system controls fuel pressure by a mechanical means, which is the fuel pressure regulator. So that regulator has got a spring and a diaphragm in there, and by adjusting that spring and diaphragm, we can actually set the fuel pressure and it'll stay there permanently. It has got a reference port there for boosted vehicles. So if you've got a boosted vehicle, it'll take some boost reference there, and it'll adjust accordingly for the boost reference. So that, just to simplify it, a return system has its pressure adjusted mechanically by the fuel pressure regulator. That's what we're going to test first. Beyond that, for test number 2, we're going to remove the fuel pressure regulator, and we're going to run the system solely on our PWM controller. So the PWM controller, if you can think of it as an electronic fuel pressure regulator, it actually electronically controls the pressure that the pump is able to deliver. So firstly, we're going to set the mechanical regulator to 58 pound, run the system. On the second test, we're going to set our controller to run the system at 58 pound electronically. Now that sounds great. It sounds, why would you want to do one or the other? Well, what we're testing for here today is the advantages of the electronic controller. Okay, we're going to see what heat is produced by running a mechanical system. Now the reason for that is we have to run the mechanical system at 100%. There's no electronics that will run the pumps down to 30% or 40%. The mechanical system is run at 100% voltage and then controlled by the mechanical regulator. The electronic system is run at 30, 40, 50, 60, 70, varying percent of voltage. You know, it can run down to 6 voltage to control the pressure. Now, what does that do to the fuel? If you're running your pumps at 100% voltage, in other words, vehicle voltage is 13.5, to 14.7, there's going to be a lot more heat transfer from your pumps into the fuel. If you're running your system by an electronic means, a PWM, and you're running it at say 6 or 7 volts at idle, you're going to have very low heat transferred into the fuel. So we're going to prove that by doing it before a regulator test by mechanical means and a regulated test by electronic means. So let's set the system up. Let's set it to 58 pound. give the pumps 100% voltage, which is about 13.5 to 14 volt, your vehicle voltage. And we're going to run them for 1 hour. We'll have a stopwatch set up there, run them for 1 hour. We'll start at the base setting and we'll go from there and see what results we get. All right, so the system's been running 2.5 minutes now. You saw that we started at 74, 75 degrees Fahrenheit. Fuel pressure is set at 58, 59. Let's just get a spot on the 58 there. Okay, 58 pound. Now we're running, this is the fuel flow in litres per hour. You can see we're running about 86 litres per hour. Just to give you some sort of reference, 86 litres per hour is about, it's a decent amount of throttle. Your light throttle going to mid throttle. So this is when we're really heating the system up the most because most of the fuel is returning back to the tank. It's not getting used by your engine. So we've set it at a low flow rate to show you its quickest rate of heating, and also where you're going to be 90% of the time, anywhere from idle to mid-range throttle. And that's where you're going to heat the fuel in the fuel tank up. So that's on 56 minutes to go now. We've gone up by about 2 or 3 degrees already. We'll come back halfway, see how we go, and we'll come back in an hour's time and let's see what results we get by running your mechanical fuel system return at about idle to mid-range to mid-load at 58 pounds, and let's see how that heats up. Okay, we've come in just after the halfway mark. It's 34 minutes gone, 26 minutes to go for our 1 hour test on our return system. Quick note, we're using water in this system as our test fluid. This cabinet needs to run water. We don't get fumes, and it keeps everything safe. So we're running water as our test fluid. What water does is transfers heat twice as slowly. So any results we're getting are pretty much twice as slow as they normally would happen. Our fuel temperature has gone from 74, I think it was, degrees Fahrenheit when we started. We're at 99 degrees Fahrenheit. And that's after about 35 minutes of running. So it's going to be very interesting to see where we get to at 1 hour's time. So you see in 25 minutes. Alrighty, here we are. We're at 2.5 minutes to go. So we're just about there. That's close to an hour now, a couple of minutes off. And we've just ticked over right then to 109 degrees Fahrenheit. So that's a decent increase in an hour of running that return system. We can also see the condensation. Once again, this is water as a testing fluid, but it's telling you the condensation that's building up in there, and also the vaporizing, the loss of fluid from that. Now, fuel starts to vaporize at about 100 degrees onwards. So for 100 degrees Celsius, you start to lose fuel in your fuel tank. And we can actually, if that was petrol or gasoline, that would be doing exactly the same thing, because we're at 109 degrees Fahrenheit. So in essence, that would be vaporizing in your tank and losing that amount of fuel. What's also happened, interestingly enough, we've dropped off on our fuel flow meter. That's because there's vapor going through our electronic meter. It's a turbine style flow meter, and it's picking up fuel, but then vapor, therefore unable to read at that lower fuel flow now. So, you know, to get a reading now, I need to ramp up the fuel flow. Here we go. So everything's starting to change. The consistency, the vaporization in the fuel, and that's after an hour. Don't forget that's water. This would have been half an hour with gasoline. Let's strip this, put some cool fresh water or fluid in there, and let's see what it does with a PWM controlled system. Alrighty, here we are back again. Everything's cleaned up now. We've gotten rid of all the plumbing from the return system, disconnected the regulator. Now we've just got the system running as a PWM controlled. We've set it to around 58 PSI, around about the same level of flow, 72 litres per hour, which is your mid-range, mid-load, going down to idle. That's why we're heating the fuel the most. And we've just got a direct feed system to the engine. Therefore, the PWM controller controls the voltage going to the module to keep the pressure. Now that changes reading at 100 times per second. So regardless of what you do, it's got to keep that pressure correct. Now, as you can see, we're now introducing not 100% duty cycle, but to keep that flow rate and to keep that pressure, the PWM controller knows to only give around 35 to 40% duty cycle. And you can see that on the screen here, 35% duty cycle, that equates to something like 6 or 7 volts input. So we should see less transfer of heat to the test fluid or fuel, ultimately gasoline. So let's start that timer. Let's put it for 1 hour again. Here we go, 1 hour. We started off, it's just gone up a degree slightly to 75. We've got our 72 litres per hour, 58 pound of pressure, exactly as we had it with the return fuel system. One thing I did forget to mention, ambient temperature, and it's a controlled room by the way, it's our fuel lab room. It's 18 degrees Celsius. I'm not sure what that is in Fahrenheit, but it's a controlled temperature. So we're starting off at the same temperature. The other test was just done an hour ago. We've changed the fluid. Here we go again. We'll see you in half an hour. Okay, I'm back again. It's almost 1 hour. It's 58 minutes since we started the PWM test, and I couldn't wait to get back in to see the results. So that's why I'm here a little bit early, but fantastic results. Actually better than I expected. With our KPM controller, we've gone up from 74 degrees from a dead cold start, which was pretty much the ambient temp of the room. We've gone up 74, we've gone up 8 degrees in 1 hour of fuel. You can see there's no condensation, there's no vaporizing. The fuel's absolutely dense and cool. Now the other thing that's a real telltale for me is the flow meter is pretty much exactly how we set it at 72 litres per hour. If you remember when we did the return system, the fuel got hot, 109 degrees, it vaporized, and I actually lost readings on my flow meter because of the vapor, the intermediate vapor and fuel caused my flow meter to become erratic. That's really important. Tuners will know this. On a vehicle, when you get hot fuel, you've got sensors on your fuel line, and those sensors will start becoming erratic because of vapor, things like fuel pressure sensor. That becomes erratic and it makes tuning problematic. Cool dense fuel is the key to ease of tuning, exact tuning, and more power. So I hope this little test proves to you that a PWM controlled system runs fuel much cooler, much denser than a return style system. I hope that puts that to bed, guys. It is the way to go. Great results. Okay, so you can see what a difference that's making. The two big pumps heating the fuel up is a problem. And you can see by using a mechanical regulator, we have to run the pumps flat out and generate a lot of heat transfer into the fuel. By using an electronic PWM to regulate the pressure, we're generating very little heat. Now, that's at the time that you're using the vehicle the most, which is 90% of your time between idle and mid-range. So you could drive to the racetrack, which is 300 mile away, go down the track and you'll still have cool fuel. So that's the advantages from that big difference in fuel. Now, the other advantage is obviously, why do OE use a electronically controlled PWM? Well, you can see the condensation, you can see the evaporation, you can see that you're losing fuel from evaporation. So all those considerations, the OE engineers know that a mechanical return system creates heat, Therefore, to reduce all of those factors, they put in an electronic PWM system. Less to nil vapor, less to nil fuel loss. Now that's great for us, definitely good for us who want the horsepower. But what's also a benefit, we retain the energy in fuel. Cool, dense fuel creates power. As soon as you start getting hotter fuel, your tunability goes out the window. The amount of energy that you can get from one drop of fuel goes down. So there's the big factor for us guys. Now this system is available for all your modern cars, for your Mustangs, for your Camaro, Gen 5, Gen 6. We're now developing the Hellcat, for the Trackhawk, for the Jeep Grand Cherokee. Guys, it's available from KPM Motorsport. We are the leaders and innovators of this system. It is the way to go. Fuss-free, fit it, no return plumbing, direct feed, up to 2,700 horsepower modular systems. It's the way to go. The OE engineers know it. That's why the cars around the world, all the performance vehicles, they haven't got a return system. That is a great means to an end, but they've gone forward now. They're using the direct systems, the Lamborghinis, your Corvettes, your Dodge direct feed system, cool fuel, drivable daily. That's what we're after. Get to the racetrack, bang, up to 2,700 horsepower. Guys, I thank you for watching. We'll do more of these videos. If you've got any questions, just ask Dave. Thanks.